For this question, we have population being studied, and we find predatory animals vary periodically, which means that we're going to have a sinusoidal function. Assume the population of foxes in a certain forest varies sinusoidally with time. So we're going to have either a sine or a cosine function that we write. Sinusoidally means sine or cosine. Records started being kept when time t was 0. A minimum number of foxes, 200 foxes, existed when t was 2.9. So I'm going to say t is 2.9, 200 foxes. The next maximum, the very next maximum, occurred at 5.1 years, and we had 800 foxes. And the question says sketch a graph and write an equation for the number of foxes as a function of time. Predict the population when t is 7, and then predict some things about endangered years. So, in order to write our equation and sketch our graph, we need to figure out the period, the amplitude, the center line, and the phase shift. So, let's take a look at this. We have a minimum of 200 when t is 2.9 years. We have a maximum when t is 5.1 years. So we have something doing like this. And then it's going to come back down, and it's going to go back up. So this difference here, that's half of a period. That's half of a wave. So if I came back down, that would be a full period. So in order to find our full period, if we subtract 5.1 years and subtract 2.9 from that, we get 2.2. That's half of the period. That means that the period is 4.4 years. So when I start to think about my graph here, I know that on my y-axis, I need to be 200 near the bottom, 800 near the top, depending on what my scale is. And so I'm going to just start counting like this. I'll put 200 here, and we'll go up 300, 400, 500, 600, 700, 800. Okay? And I think because of these numbers, they're fairly straightforward. You could probably see 500 is in the middle. But how would we get that? Well, we would say that the max plus the min over 2, that's going to be the center line. That's going to be D. So if we do 200 plus 800 over 2, we see that D is equal to 500. So that's our middle line, the 500. Now, the max minus D gives us our A. So if we want to do our calculation, the max value minus D equals A, we can find that 800 minus 500 equals A. So A equals 300. So now we have our A for our equation. We have our D for our equation. We have the period. So, sorry about that. Finish this up here quick. So for the period, B is equal to 2 pi over the period. So we can say that B is going to equal 2 pi over 4.4. And you can just leave it like that, or you can approximate it. When you do that on your calculator, you get that that's approximately 1.43. And for this modeling problem, that's okay to approximate it as well. So we'll use that for B. And so we can start to sketch in our graph now. We have 500 as our center line. And we know that we have to have a period of 4.4 years. So in this case, I'm just going to go by 0.5s. 0.5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So every 2 blocks is 1, because I have some real data to put on. So I'm going to put at 2.9 years, we're at 200. At 5.1 years, we're at 800. Now, I could add 2.2 to the 5.1, right? 5.1 plus a half of a period is 7.3. I should be back down to the minimum, about here. Okay, and you'll start to see your graph. Now, I would like to write an equation. It's asking me for an equation. So if I take my 2.9 and I subtract another half a period, I find that at 0.7, I'm back at the top. And that's helpful because that means I can pick this up for my phase shift, because that's going to be the top of a cosine graph. And that's the closest one to 0, and it's nice to get the closest one to 0. It's not essential, But that point there is the first top, the first max, and so I'm going to use that as my phase shift for my equation. Now, remember, we can write the equation two ways, and when we're trying to write the equation from a graph that we have, the easier way to write it is f of x is equal to a cosine, you could pick sine if you wanted to, b, parentheses b, and then another parentheses x minus h, double parenthesis close, plus d. Because this way you can just read the phase shift right from the graph, and we can see, based on our calculation, that that's going to be 0.7. So we have a is 300 cosine, b is 1.43, x minus 0.7, and we keep the minus because it's a shift to the right, plus 500. And that's the equation that models the population of foxes, where x is the time axis, or the population of predators. So the next question says, predict the population when t is 7. So I'm going to show you on the calculator. We want to go over here and say, when t is 7, what's the population here? So it should be down closer to the 200 range. So I've plugged in the equation on the calculator. 300 cosine, parentheses, 1.43, another parentheses, x minus 0.7, and then I have to close both of those parentheses, and then plus 500. And if you graph that, you get the wave. And so you can see at 2.9 we're at a low. At 5.1 you're at a max. So we want to know when x is 7, what's the population? So we can just do a quick calc value. When x is 7, what's the y value? Well, y is 225.5. So when x is 7, you're going to have 225 or 226 foxes. Okay. Next question says, when the foxes are declared to be an endangered species when their population drops below 300. So that means I want to draw a line in here at 300 and see at what time is my fox population below 300. So we'll go back to y equals, and we'll put 300, and we'll graph that again. And now we can see the first time that it drops below 300 is here, and then it comes back above 300 here. So let's see, between what two non-negative values of t were the foxes endangered? So we're going to do a calc intersect, and we're going to try to find that point right there. So we'll bring this over closer to that intersection point. So there, yep, and the intersection is when x is 2.3 years. So at year 2.3, it drops below, and let's see when it comes back out of it. So this point right here. So we're going to do second calc intersect again.